Hi everyone, my name is Ajalo Benigdos. So for today's video, I am gonna report together with my partner, Miss Chiki Belhera, about the designing complex systems for the subject of HPC 212 supply chain management, and we are the BSHM2C.
Objectives. At the end of this lesson, everyone should know about the different types of designing complex system. Introduction: Designing complex system. According to E. Morin, who is considered as the father of complex thinking, complex comes from complexus, which means what is braided together or woven together. We cannot deduce the overall system functioning by the addition of the subsystem or parts that compose it. Several techniques currently exist to design complex systems. The most common technique used is to divide complex systems into smaller modules or subsystems. Build the modules separately and later integrate them. In this lesson, we will learn about how these systems should be designed. First, socio-technical system. They have adapted to changing economic conditions, societal demands, and end-user requirements. The development of Europe's critical infrastructure is not certainly planned and coordinated but governed by many actors who optimize their management decisions and investment strategies for their own subsystem. Complex system design may therefore be considered a contradiction in terms. How should the future complex system be modeled? How should the design process be set up among this multitude of actors, and who, if anyone, are they responsible for the overall design and design process? Complex infrastructure system. Infrastructure system as socio-technical system. The notion of infrastructure generally refers only to the physical network that connects the suppliers and end users of an infrastructure-bound service. Any infrastructure is in itself a highly complex network system that includes both a physical and social network or actor network. So here's the domain of complexity in infrastructure. The physical network and the social network are complex in themselves, and their interaction at the level of the integrated socio-technical system represents another domain of complexity. The physical network and the social network are complex in themselves, and their interaction at the level of the integrated socio-technical system presents another domain of complexity. Complexity in the physical network. The physical networks of infrastructure system consist of many nodes and links. Large-scale systems, such as the European electricity infrastructure, comprise a huge number of subsystems, links, and nodes, all of which are interdependent in several ways. In addition, the actors are interdependent. That's why each of them needs the cooperation of the other actors. Complexity in the social network. In a multi-actor system, such as the European electric power infrastructure, many actors are involved with different, possibly conflicting, interests, and hence different perception and reality. Agents may be used to model the system's elements. which in the case are people and organizations. In analogy with the agents in the physical network, each actor in the social network can be described as an agent that acts according to a set of rules determined by legislation and regulation, moral and cultural codes, etc. Evaluation of infrastructure system. Part of problem with understanding the behavior of infrastructure in that most of the physical system were not designed as an integrated system, but gradually evolved over time. A typical example in the way of the electricity infrastructure evolved in, in the Netherlands. Like most infrastructure, originated in local networks established through private initiative. The infrastructure value chain was fully integrated vertically, as you can see at the picture on the left side. This was justified by the fact that the transport and distribution network have the character of the natural monopoly. While at the right side, this transition does not directly impact the technical network, but mainly the social network.
Before we talk about of complex systems, let me start by thinking a bit about design itself and our traditional approach to it. Design and engineering are very broad and fundamental human activities, and there are a lot of different definitions for them. But at the heart of many of these definitions is design as a process that is a process where we conceive of an original or improved solutions to achieving some desired optimal end state. Then we identify the set of factors and constraints without the given environment. And lastly, developing a model or the arrangement of a set of elements to achieving the desired end state that is the design. Thus, whether we are engineering a bicycle new production process for the factory or designing some healthcare service, we can say design is about the arrangement of elements within a system in order to achieve some optimal global functionality. With engineering, this optical functionality is typically talked about and quantified in terms of systems efficiency. A design paradigm then is overarching about how the world we want to engineer works, coupled with a complementary set of principles and methods with which to approach that design process. Like many other areas, our modern engineering paradigm inherits theoretical foundations from the modern science and in particular classical physics. A key method employed by both is that reductionism. Reductionism holds that a complex system is nothing but the sum of its parts and that an account it can be reduced to accounts of its individual constituents. The reductionist approach results in a vision of the world that is made up of isolated components that interact in a predetermined linear fashion. What is sometimes called the clockwork universe, as we put reductionist goggles on, everything starts to look like little deterministic cogs in a vast machine. Thus, the reductionist approach applied to engineering results in the decomposing or breaking down of a whole systems into discrete components that can be isolated and modeled using linear equations. The overall functionality of the system is then achieved by defining an overarching top-down plan as to how all these components will fit back together in order to achieve this. Overall, the functionality of the systems, it is important that the elements can be constrained. That is to say, they are relatively static and their behavior can be predetermined and thus controlled. The reductionist approach has worked well in the engineering of bridges, airplanes, and skyscrapers. These systems are designed to be, and we want them to be stable, predictable, and reliable. Reductionism works well when we are dealing with systems with a low level of interconnectivity and interdependence. where the components are static, controllable, and the environment relatively unchanging. But what happens when this is not the case, where we have to design information systems where the components are highly interconnected and interdependent? So when we have to build sustainable cities with multiple stakeholders that all have their own agendas or infrastructure, systems that will have to operate in unchanging, uncertain future environment created by the climate change. In this case, our basic assumptions or design paradigm has to shift to one that is more focused upon the connections that integrate diverse components into systems as opposed to our traditional components based paradigm. And this is where complex systems designs comes in. So let's talk about the key features to this new design paradigm, all of which will be major themes throughout the rest of the course. Firstly, complex systems are open systems. In traditional design and engineering, we are dealing with things like chairs, bridges, and buildings. They have well-defined boundaries. We can fully control all the elements within those boundaries and fully design the systems. This makes them orderly and predictable. With the design of complex systems, what we're dealing with instead are open systems, think of electrical power grids, cities, or the internet. It's a massively modular distributed system that has no defined boundaries. People and devices couple and decouple from the systems. It is not random, but this world of complex systems is not so orderly. It is, to use the catchy phrase, edge of chaos. No one is controlled and no one fully understands or can fully design their open systems. To summarize, we can say complex systems design represents as an alternative paradigm to our traditional design engineering approach. This traditional paradigm is focused upon the development of discrete, well-defined objects by breaking them down into individual components and then coordinating these components with one top-down global design. These systems are designed to be static, stable, and operate predictably within well-defined parameters. In contrary, we have seen how the paradigm of complex systems design is focused on the development of open systems that integrate diverse components through a dynamic network, and that global functionality emerges from the bottom-up as elements interact, adapt, and evolve over time. Classical examples of this are the complex engineered systems or the internet and cities, but also healthcare systems, electrical power grids, financial portfolios, logistic networks, and transportation networks.